Hello calculus students, today we'll be doing volumes of solids of known cross-section. Alright, in the image below, imagine that this is a depiction of some sort of solid through which there's some sort of axis. There's a back edge here. If you can imagine rotating this thing around, there's just a three-dimensional solid. If it turns out that we could slice through this solid like through a loaf of bread and make a bunch of slices, imagine one such slice, and the slices don't have to be circular in shape. Imagine that one slice, I don't know, and then it dips back here. They don't have to be circles necessarily. And if we happen to know the cross-sectional area, so the area of the face of that slice, let's say it has an area and it's a function of x. Furthermore, let's say that the slicing starts at x equals a and ends at x equals b. So as you do different slices from A to B, you get different cross-sectional areas. So the cross-sectional area will be a function of x. And of course, the thickness of the slice has a little bit of thickness. We'll call that the dx, or the delta x. And if I was going to give a formula for the volume of this slice, volume would be a function of x, and it would be found by doing the cross-sectional area times that delta x. But this is a general formula, and the cross-sectional area would change as you looked at different slices. But the volume of the entire solid that we see here from A to B is going to be the sum of the volumes of all the slices. So we do a sum, an integral, S, of the cross-sectional areas times the delta x, which will be the dx in the integral context. And then we're going to integrate from x equals A to x equals B. And this is how we can find the volume of a solid whose cross-section has a known area. So as our first example, consider a solid that has a flat base, right? So unlike this solid had flat ends. We'll call these the ends, but imagine it was sitting on like a tabletop, and this particular drawing, I don't see a flat base. I see a curving base, like a vase tipped on its side, right? It wouldn't have a flat base. But in this example, we're imagining a solid has a flat base. And that base is the region bounded by the curves below. Cross-sections that are perpendicular to the x-axis are squares. The red is y equals 2, the blue is y equals sine of x, and we're between 0 and pi, are the vertical lines, the green and the purple. And so this is the region that is the base of our solid. So now you have to imagine like that's a tabletop and some solid is coming out of it. So there's our region, that's the base. And then if you're trying to find the area of this, you can imagine you would do a bunch of vertical slices across here. But now imagine that we're slicing through a three-dimensional object whose base is that region. So I'm going to be able to tilt this on its side and look at it from an angle. And each slice makes the cross-section that is the shape of a square. And clearly you can see that as the region tapers in the middle, that the squares also would change size. Imagine a 3D solid where all the cross-sections are these squares. It's like a bizarre loaf of bread, if you will, that we're going to slice through. This is the solid whose volume we're trying to find. In my work here, I'm going to do some visual representations of what we saw with the technology. So I'm going to make a graph of the base looking straight down at it. So here's y equals 2. Here's the sine curve doing something like this. You have the right and left boundaries are x equals 0 and x equals pi. And imagine that we're going to slice through the solid perpendicular to the x-axis, so that means a vertical slice. Okay, its thickness is going to be the delta x, or the dx, we can say. But we do want to figure out how long it is. We'll call this L of x. Because when I imagine now this thing drawn on its side, all right, so I'm trying to draw this thing viewed from an angle. And I'm going to put our L slice, and then sitting on top of this would be a square. Well, if I know that the base is L, then since this is a square, the height is also L, and then the thickness is the dx. V sub slice will be equal to L times L, or L squared, and then times the thickness dx. If there are some units here involved, which there aren't, but if everything was in feet, for example, then it would be feet times feet times feet. You'd have cubic feet. It would be the volume of that slice. It's good to be able to draw both of these pictures. If not both, then I would focus on maybe trying to draw this one here, so you have a good sense for what it is you're trying to accomplish. And now let's do the volume of the entire solid. So the volume of the entire solid will be an integral from x equals 0 to x equals pi. So that's where the slicing will start and stop, and those are x coordinates. And we simply put the cross-sectional area, the cross-sectional area is the L squared, and then times the dx gives us the volume. So if you're looking back at this formula here, this part here would be the L squared, and this part here would be the thickness, the dx. But when you multiply the area times the thickness, that's a volume, and then you add them all up and you get the total volume. All right, so one thing we want to do then is establish what L is as a function. Well, the length of that strip is the upper function minus the lower function. The upper function is a constant and the lower function is sine of x. So as x varies from 0 to pi, L will change according to this function. So you could come down here and replace the L with that expression, 2 minus sine of x, and that needs to be squared because it's L times L, and then times the thickness. Again, this here is the cross-sectional area. This is a volume. So once we have the volume of the slice, which is 2 minus sine of x, and that's being squared, and then dx. Now we just do the integral of that, which means add them up from all the slices, all the volumes from 0 to pi. Now in order to finish this integral, we have to do some foiling. So our volume is going to be the integral from 0 to pi. When you FOIL this, you get 4 minus 4 sine x plus sine squared of x. This I can integrate, but this requires the power reducing identity. So I'm not going to do any integration until I'm fully prepped with everything. So the power reducing identity for sine squared is 1/2 and then 1 minus cosine of 2x. Then I'm going to distribute the 1/2 and combine the 1/2 I'm going to get right there with that 4. So I'm going to do a few steps here to determine how this continues to simplify. 4 plus 1/2, that's 8 halves plus 1/2, that's going to be 9 halves, minus 4 sine x, and then minus 1/2 cosine 2x. I think we're ready to integrate one at a time. So integrate the 9 halves, that's going to give us 9 halves x. Integrate the negative 4 sine x, that's going to be positive 4 cosine x. And integrate the 1/2 cosine 2x. Integral of negative cosine will be negative sine. I'm going to have to divide by another 2 to reverse that chain rule that would happen. So we should have a negative 1/4 sine 2x. If you're not sure you did that antiderivative correctly, then differentiate this and see if you get to there. Then we're going to evaluate this from 0 to pi. So we get 9 halves times pi plus 4 times cosine of pi. Cosine of pi is negative 1. So this will actually just be minus 4. Sine of 2 pi is 0. So we can get a minus 0 there, and this is plugging in pi, and then minus, and I'll plug in 0. We get 0 times 9 halves is 0, but cosine of 0 is 1, so there's going to be a plus of 4 there. And sine of 0 is 0. And then when I distribute the negative, in the end, I'm getting 9 halves times pi minus 8. And this would be a cubic unit. Whatever these units were, if they were measured in feet, then this would be cubic feet. And then if you reach for a calculator and decimalize this, you get about 6.137. Okay, let's do a similar problem. It's going to be the same base, the same 4 curves that define the base. However, this time the cross sections that are perpendicular to the x-axis will be semicircles. And you can see that as you slice through the region now, we're going to expect to see semicircles and try to imagine what this solid would look like. This time around, I'm only going to redraw the bottom picture. And let's put depiction of some sort of semicircle that has a little bit of thickness. Right, drawing doesn't have to be perfect. Now, we do have the base is L. And let's see if we can come up with the volume of this slice. Well, if I knew the cross-sectional area, which is half of a circle whose diameter is L, right, if you're looking at a complete circle straight on, and you know that that length is L, then you would want to find the radius by cutting L in half, and then doing pi r squared. And then if you only wanted half of that, then you'd cut it in half, right? So this is my strategy here. So the volume of this slice will be equal to pi radius squared. That'll give me the area of a full circle. Cut that in half. That'll give me the area of half of a circle. And then times the dx will give me the volume of the slice. Okay, now the radius of the circle is L halves. So I could replace this with L halves and then put a square. Now I can square the L and square the 2 in the denominator, get a 4. So I could write this instead now as, it's going to wind up being 1/8, right? Because we're going to have a 1/4 combining with the 1/2, multiplying with the 1/2, pi L squared dx. And since I know what L is, I go back up to here, right? L is equal, in terms of x anyway, L is 2 minus the sine of x. I can now finally express the volume of my slice as a function of x. And we get this result. So the volume of the entire solid will be the integral from 0 to pi 8 times 2 minus sine of x squared dx. Now I'm not going to repeat all the work we just did. This pi 8 can be factored to the front. Then I'm just going to borrow the answer we got from above. because I already actually integrated 0 to pi of 2 minus sine of x quantity squared dx. And we got this answer, so I'm just going to borrow that answer. But we do have a pi eighths in front. We're going to multiply by this answer of 9 halves of pi minus 8. And now we're going to distribute pi over 8 and see what we get. As an answer, we have a 9/16 of pi squared minus, and then 8 times pi eighths will just give us a pi there. This would be cubic units. And it turns out that in a decimal, when you reach for a calculator, this is about 2.41 cubic units. Now, if you had an intuition about which two volumes of these two problems here would be more, I hope that your intuition would have led to the second problem would have a smaller volume. Okay, just one more problem to do. A solid has a flat circular base with a radius of 3. Cross sections are equilateral triangles. Find the volume of the solid. All right, so we have some sort of flat circular base, and I'm going to do cross sections. It doesn't say whether they should be perpendicular to the x-axis or y-axis. We do want them to be perpendicular to the base. And if you were to look at this from the side, and I'm going to try to draw a slice, keep in mind that there's some sort of solid coming up out of the ground here, and they're equilateral triangles. So there would be some sort of triangle sitting on top of that. But just to illustrate what you should be imagining, right, as you do slices through the solid and you see equilateral triangles the whole time, it'd be some sort of effect like you're seeing here. Okay, so we're going to have to do some review of some ideas. Let's situate this circle in the context of an x and y axis. So I'm going to imagine an x-axis going right through here. To get the equation of a circle whose radius is 3 and whose center is at the origin, so the radius is 3, so we're going through the point 3, 0, center is at the origin. The equation for such a circle is x squared plus y squared equals radius squared. So in this case it would equal 3 squared, or 9. Now let's go to Desmos and explore this a little bit. And let me type that in. X squared plus y squared equals 9. You can see our circle centered at the origin, radius is 3. If you were to take this equation and solve it for y, let me do that by hand over here. Okay, so I'm going to solve for y squared first by subtracting the x squared to the right and then square root both sides. Now make sure you do not do square root the 9 and square root the x separately and say something like this. This is not correct. You can't square root a difference by square rooting the terms. So the best we're going to say is y is plus or minus the square root of 9 minus x squared. Let's type those into Desmos and see what we get when I say y equals the square root of 9 minus x squared. Notice what got graphed. We got the top half of that same circle. Whereas if I put a minus sign in front of there, we get the bottom half. So when you put them together, the plus and the minus, you get both halves. You get the whole circle. Okay, so what that means is I'm going to go over to here, get rid of that circle there. And let's focus on just keeping the top half. The top half of this circle, whose radius is 3, so this is starting at -3 and ending at +3. Make that one red. The equation for that is y is equal to the positive square root of 9 minus x squared. This is the function way to describe the top half of a circle of radius 3 centered at the origin. Next thing I want to do is, well, how long is this strip? Let's call that L. Well, the bottom half of the circle is the negative radical. So if I do top function minus bottom function, it would look something like this. Top function minus bottom function. And notice what would happen. This would just become addition, and you'd be adding the same thing. You'd get 2 of these radicals, would be our L. We can establish this by symmetry, because if you do top half minus 0, then I'm finding half the length of L. Right? I'd be going from this function down to the x-axis, and minusing 0, of course, doesn't change anything. So this length right here is half of our L. So if I double it, I'll get L. And you can see that by doubling half of it, or by doing top minus bottom, where the bottom is the negative radical. Either way that we do this, we're arriving at the conclusion that the L in this picture, the length of that strip, is double this function. We'll sit on that for now and come back to it in a moment. So in this picture here, where we see the triangle, it's an L by L by L triangle. It's an equilateral triangle. So now we need to do a little bit of review about how to find the area of an equilateral triangle if I know all 3 sides. So let me draw a triangle over here that's equilateral. And let's say that we know that all the sides are L. How do we find the area of this triangle? Well, imagine cutting it right down the middle. And let's do half of this. Okay, so here's my equilateral triangle, but half of it. This would be L. Let's call this H for the height, and down here would be L halves. So if I want to figure out the H, then I could do Pythagorean theorem and say that H squared plus L halves squared equals hypotenuse squared. So we get H squared is equal to L squared minus, and then this one is L squared over 4. Get a common denominator, so make this be a 4 over 4 and subtract those. We get H squared is equal to 3L squared over 4, and then I'll take the square root. So we get H is equal to, and when you square root all of that, you get a square root the 3, the L squared, and the 4 separately. There's going to be an L involved, there's going to be a radical 3 involved, and all over it too. Now I don't know if you remember your ratios of sides when it comes to a 30, 60, 90 triangle, because this triangle up here is equilateral, so that's 60 degrees, this is 60 degrees, etc. That's going to be a right angle. So this is a 30, 60, 90 right triangle that's depicted down below. And if you recall, if you know the hypotenuse, it's always true that the shorter side is half the hypotenuse, and then the longer leg is radical 3 times the shorter leg, which is what you're seeing right here. Now we want to go over here and say, okay, what's the volume of this slice? Well, the volume of the slice is going to be the area of the triangular cross-section times the thickness dx. And if you recall how you find the area of a triangle, you do 1/2 base times height. Of course, this triangle that I just circled, we'd want to double that to get this triangle. That's the area I'm actually after. So if I just do this times this, I should get the area of this whole triangle. So we get L halves times H will be the area of the equilateral triangle, and then times the thickness dx. Now I want to express this though as a function of x. I don't want these other letters L and H, but since I can first change H into terms of L, right, because we determined that H is L times radical 3 over 2. So I could say that in the end this is radical 3 over 4 times L squared times dx. And now I can replace L with its function, which we determined up here. So this winds up being radical 3 over 4 times L, which is 2 times radical 9 minus x squared dx. Oh, I need to square that. And when you square both parts of that, you get 4 times 9 minus x squared, but then the 4 is going to cancel. In the end, you just get radical 3 times parentheses 9 minus x squared. No more square root in dx. Right, that's the volume of the slice. I'm going to finish this problem using Desmos as an integral calculator, so the total volume of this solid will be an integral. So I look back up to this image here, right? I'm integrating -3 to +3, and then we put the volume of the slice formula that we just determined, which is radical 3 times 9 minus x squared and parentheses dx. Okay, this will do it. And if you leave off the radical 3 and just plug in this part here in Desmos and do an integral, you're going to get 36, but then times the radical 3. So we do get 36 radical 3. These would be cubic units. Reach for a calculator to decimalize this. It's about 62.354 cubic units would be the volume of this one. All right, so this example showed us several things that maybe you were a little bit rusty on. That first thing being, hey, what happens if you are working with a circle and you want to just look at the top half of it as a function? And also a thing that we reviewed was how to do a little bit of geometry with some equilateral triangles. And that's it